I'm Kara. Some of you know me, some of you don't probably. I'm just taking over this talk for the adaptive management of the reintroduced species, because adaptive management is a type of management that focuses on learning. This helps us learn from the reintroductions that we undertake in order to make better predictions and therefore hopefully achieve better outcomes for future reintroductions. So adaptive management is a formal structured decision-making cycle, which is really good for use when there's uncertainty of the outcomes of the decision that has to be made. So this is ideal for reintroductions because generally there's a lot of uncertainty when you're moving species to a new site. So this gives us good structure for making the best decisions based on the knowledge we know, and then gives us a structure to learn from these decisions and the outcomes of these decisions to implement in the future. So adaptive management works in this little cycle here. There is a goal statement. So for a reintroduction, maybe that's to reintroduce birds. You define your objectives, and so that could be to have a persistent population, for example, but also might include things like keeping costs as low as possible, and develop alternative management strategies. So maybe to reintroduce or not to reintroduce if it turns out that that's not the best idea. So before you reintroduce, you can model and predict based on prior information that you know about the species you're trying to reintroduce. So this could be like vital rates, limiting factors for the species, and site aspects to do with the site, such as connectivity that Zoe and Kevin have talked about. Once you've done that, you can trade off between how that achieves your objectives and make a decision about how to proceed. For a reintroduction or translocation, you might go ahead to reintroduce the species, in which case you then move into this inner circle in the middle here of monitoring the reintroduced birds or animals or plants. And you can use Bayesian methods to update the prior models that you made initial predictions with. And what this can do is increase the accuracy of the population predictions, which you can then use to inform any management decisions and have a more informed decision of what is best. So this monitoring, update models, and revise alternatives section is really what sets adaptive management apart from other management strategies, because this is the part where you're learning and you're taking into account that new information that you've learned. So there are 3 stages to this, and we can use Bayesian methods to help combine information to get more accurate or more certain results. So on the proposal stage, models can be built from data collected from previous sites, and predictions can be made about what might happen to your reintroduced individuals. These data can be combined in Bayesian methods to make more accurate predictions than if you're only using data from one site. Once you have reintroduced or translocated individuals, you can collect site-specific data through monitoring methods for the individuals and for things like rats. In New Zealand, many of our species that we're reintroducing are limited by rats or other pests, and that can be taken into account too. This data can then be combined with the prior models or the prior data that you had using Bayesian methods, which can again increase the accuracy of predictions and allow for more informed management decisions to then be made. And the benefit of this is that you then have an even more accurate, or a model that can create potentially more accurate predictions for future reintroductions, which means decisions around future reintroductions can be more informed. So before you initially create models, you want to consider explicit models such as this in order to get more specific and quantitative information. So this example here is for totoi, which is the main species I've worked with and has the advantage of quite a big and good data set from lots of sites. So we know that predator density, which represented by rat tracking rate in this case, and connectivity are predictors of reintroduced totoi population persistence. These things affect the vital parameters of the population, so the fecundity and the survival and the juvenile recruitment into the population. This model here shows adult females because they're the limiting sex. We know that birth rate along the bottom there is strongly declines with rat numbers because eggs and chicks are vulnerable to rat predation in the nest. Adult female survival, the little loop at the top there, also declines with rats as rats increase because of predation when they're sitting on nests, and the juvenile recruitment into the population declines with connectivity because they disperse out of the managed area, as Zoe was saying. So once you've created your explicit population model, you can use population data to make predictions under different scenarios. For totoi, Liz, Pilata, and Doug used data from 10 previous reintroduction sites combined in a Bayesian hierarchical model to make predictions about the likely outcomes of a reintroduction to a new site. So that was Pukaha in the paper that they did back in 2012. This is the model and predict section of that adaptive management cycle that I showed at the back. So on this graph, we have lambda here, which is the finite rate of increase of the population. And pretty much lambda of 1 means you have a stable population, lower than 1 means you have a declining population, and higher than 1 means that your population is growing, obviously. The higher lambda is, the faster it's growing. Here, the data from each site was modeled under different tracking rates and lambda estimated. Using Bayesian methods, they were able to combine the data from each site to make predictions for the proposed site. This model here has been used as prior information for several totoi reintroductions now, and most attention paid to the information from it was used in formal decision making for the Taranaki manga reintroduction and the Turatea reintroduction. So the totoi were reintroduced to Taranaki manga in 2017, and Zoe's covered a bit of this, so I'll just touch on it briefly, as I wasn't directly involved with this either. So the site had pretty low tracking rate, but high connectivity to the surrounding area that had the less intensive predator control. The population prediction for the 5 years after release is shown on this little graph here, with the bold line showing the median prediction and the dashed line showing the 95% prediction intervals. The model is built from data with those 10 sites on the previous slide, and this showed that there was a good chance of population persistence and growth at the site with current management, which is what guided the decision to reintroduce. Doug and Zoe and the others have recently published a paper on updating of this prior model with the Bayesian methods from data collected after release. So these graphs at the right here show how understanding of parameters differs depending on whether you just use the prior data, which is in red, or combine them, which is in or site-specific data, sorry, which is in blue on some of the graphs there, the bottom two, or combine them, which is in purple. So the combined data has the advantage of being more certain compared to the site data, which is just from a small data set. So we can see they're quite similar predictions for a lot of these, but the uncertainty in these results is decreased for the combined data, which is why we tend to use that for decision making moving forward with management. The central bottom graph there just shows how the results were used to inform management about the necessary size of the managed area and the intensity of control needed, so accounting for the dispersal behaviour of the birds. So in 2018, the Doug and Liz's model, built from other sites and data, was used to make predictions for a potential reintroduction to Turitea Reserve in Palmerston North. So this reserve's had intensive predator control for over 20 years now and has, as Zoe said, has had a rat tracking rate of about 20%, fluctuating around 20% for quite a long time. Has moderate connectivity, like quite high, but less than Taranaki, which is completely joined to the unmanaged areas. While with our little prediction graph down the bottom here, while there was some uncertainty that, sorry, I'm a bit lost. Yeah, the little prediction graph at the bottom, so not quite as much of growth predicted for Turitea, but still there was considered a good enough chance for the population to persist under the current management for decision makers to decide to go ahead with the reintroduction, which eventually happened in 2021 after some COVID delays. It was recognised at the time, though, that management may need to be readdressed in the future. So I took over, I kind of started doing the breeding monitoring accidentally after meeting Zoe and Doug out in the bush, and then did a whole master's project on it. So we monitor the birds' survival and fecundity using adult presence and absence every time we go out and check territories, and using the behaviour of adults to gauge what stage of nesting they're at. And at the end of the season, we can come up with a matrix like this, which shows the 1's adults being present, the 0's adults not being present when we go to check them, and then the number of fledglings produced by each female at the end here. Unfortunately, our first breeding season was not a great success. We only had 6 out of 19 nests succeed and lost 5 females and 3 males during breeding season and in the period just after breeding season. So that was not the results we were hoping for. And we can see when we use this breeding season data to update our prior models that the site-specific data in the blue here on these top 2 graphs is much lower than what the prior data predicted. The red graphs here for adult female survival and fledglings per female. But because that's just a small data set, we don't have the confidence in this to use for the decision making. So what we do is use those Bayesian methods to combine with the prior data and use that for making management decisions. So we use the adult female survival and the fledglings per female and juvenile recruitment. Juvenile recruitment into the population, although we don't have site-specific data for that after just 1 season, to estimate lambda, so the finite rate of increase in the population. And we can see that compared to the prior data, which was mean above, or median lambda was above 1, our lambda's now dropped below 1, which would predict a declining population. This suggested our management would need to change in order to increase the population's chance of survival. So we estimated that if we decreased the rat density, we could get tracking below 5%. So that would be by increasing control. And we were able to use the model to predict what that might do for our population. So we can see that that gets slightly shifts lambda to the right there with a median about just on 1. So even by decreasing the rat density in the reserve, it would still be quite uncertain whether the population would persist. the stakeholders decided that they wanted to commit to try and increase the chances of population persistence. And the best option for this, after considering alternatives, was to just increase control in the core area, as this kept costs lower than if we were increasing control reserve-wide, and all the tautuai had decided to settle in these little purple hexagons there at each of the territories for that first breeding season. As Zoe's mentioned, this took the form of primarily these striker baits over on the left here, which are diphacinone poison, and we had 20,000 of those set over winter after that first breeding season. Spacings of approximately like 20 meters or 10 meters in some places. And additionally, we had over 300 of these AT220 traps, which are the little yellow crosses on the map there, spread over a bit of a wider area, just to increase control slightly wider and maybe create a sort of buffer against reinvasion back into that core area. So we continued breeding season monitoring of the tautuai over the 2022-23 breeding season, and we're able to therefore update our models again post-breeding season. Rat tracking rate was kept below 5% in that core area and was actually 0% through the robin breeding season, although we did have a fairly small number of tunnels. We had 34 tunnels in that 280 hectare area. We had better survival over the year, losing only one female compared to the 5 the year before, and better reproduction. So the 5 females we had at the start of that second breeding season produced 13 fledglings. Juvenile survival was, we can see on the bottom left graph here, was not too much below what was predicted by the prior model. These graphs at the top show the vital rate predictions under a 5% rat tracking rate, which is the dashed line, and the old 24% rat tracking rate, while the red shows the same using just the prior information, no turitea information. Yeah, so the purple is the combined model with the additional information added. We can see that compared to the 24% rat tracking rate, survival and fecundity have improved with the lower rat density, but not by heaps and heaps. And then we can see the lambda in the bottom right over here at the lower tracking rate is better than the 24% tracking rate, but the median lambda is still predicted to be about 1, so a stable population. But still, we have so much uncertainty about whether that population will persist, because it could go either way, really. We continued monitoring over the 2023-24 breeding season with some increased tracking tunnels in that area, so that we could be more sure our rat tracking rate was accurate. And it was, so we've kept under 5% rat tracking rate for most of the year. I think it's been as low as 1%. We're using 84 tunnels. And again, we had good adult survival and good fecundity under the new management. So the red shows the prior model again under 24%, the solid line, and 5% for the dashed line estimates. And the purple shows the prior model with now 3 years of turitea data added. With each year of turitea data added, we've increased the confidence we have in the estimates. We can see, looking at lambda down in the bottom right here, that the purple dashed line, which shows our current situation, if we can maintain that rat tracking rate under 5%, is still pretty much bang on 1. So we're still really uncertain about what our population's going to do. And that's with are very, very intensive management control. So if the rat density was to increase again, we'd expect the population to start declining based on these predictions. So the other management decision we faced at the end of the 2023-24 breeding season was whether to do a reinforcement translocation to the population. Now that our survival and fecundity has been good the last few years, that we've been able to keep the rat numbers low, and the council and Rangitane have committed to continuing with that pest control for the short term at least. So this has always sort of been on the cards for this translocation, as it was in the initial proposal, but we've put it off while we're not sure whether the population can persist at that site. But yeah, it was sort of pushed by the stakeholders in the end of breeding season meeting that we had. So these graphs show the number of adult totoi present at the start of each breeding season so far, and then predicts the next 5 years with and without a reinforcement translocation of another 40 birds. The projections with reinforcement on the right there assume that 40 additional totoi are released next year, and that they have equal probability of establishing, and as the birds did in 2021, so about 50%, and there's 50% chance of a establishing bird being a male or a female. So yeah, the black lines show the median projection of the population. And we can see that with both a reinforcement or not a reinforcement, we still have the situation where our population's predicted to have a lambda of about 1 or potentially under. So still so much uncertainty. I think there's some hope that other effects, such as having a larger population size, could mean that it persists better, but we'll have to monitor after that to improve our knowledge and help decide what management may be suitable moving forward. As with all other data collected over the last 3 years, that would help inform decisions for other reintroductions and any management decisions that may have to be made for other reintroductions in the future. So basically, situations such as this, where we're doing intensive monitoring and modelling and making predictions, show that reintroductions really are quite complex endeavours, and even when you have all of those things, such high intensity monitoring, there's so much uncertainty. Like, it helps give us some understanding and to improve outcomes, but also just creates more questions that need to be answered in the future sometime. So thank you. It's me.
Thanks, Kara.